Hello, today I'm going to go over the first page in our packet and then I'm going to start the worksheets with you. We are going to start working on our unit number 6, and that's about bonding. And we have a few different kind of bondings. On this initial note sheet, we have nonpolar covalent, polar covalent, and ionic bonding. And the most important difference to know between ionic and nonpolar and polar covalent is that ionics are between a metal and a nonmetal. And remember, we have a staircase on our periodic table, so you want that out and you want to look which sides are your metals and your nonmetals. Now our covalents, co meaning sharing, they share the same side of the periodic table, and that's where all the nonmetals live. So our covalent is between two nonmetals, okay? And we call ionic compounds formula units, where polar covalent are molecules. And here's the difference. So an ionic compound is sodium chloride, okay? So NaCl, that's ionic. And we have a formula of 1 sodium and 1 chlorine. But if I look at this picture, there's a lot of atoms of sodium and a lot of atoms of chlorine going on there. And here's what's really happening. We have sodium and it has 1 valence electron, and we have chlorine that has 1, 2, 3, 4, 5, 6, 7 valence electrons. So chlorine has enough room to add 1 more. So what it does is it steals this electron from sodium, and sodium gets a full real charge of positive, and chlorine added another electron, so it's going to be negative, and it has that full H shell, okay? And then what they do is they click together electrostatically like a magnet, and that's considered an ionic bond. Now, because they behave like magnets, we can keep clicking on more sodiums and chlorines, and it goes on forever and ever and ever. But when we analyze this, we do have 1 sodium to 1 chlorine, which is why our formula is 1 to 1, and we consider that a formula unit. That is different than water, which is H2O, and that's a covalent molecule. And it's called a molecule because it's an individual piece, okay? They are separate. They don't just keep clicking over and over and forming more bonds. They might be attracted to each other, but they don't continually form more covalent bonds. Once we make that substance, it is 1 molecule. So that's a molecule where NaCl is considered a formula unit. So we have ionics click together by electrostatic attraction. That's where we steal an electron, they become charged particles, and we click together. Where covalents share electrons, and this was our Lewis-Stott model, and we will get into that in a moment, and we'll have a whole little unit on that. Now, these two things are very important. You need to know what are covalent molecules and what are ionic, because they have different properties. Remember, think about this as sodium chloride, and sodium chloride has a very high melting point. You cannot melt that even in a pan. They're strong, they're hard, they're brittle, and they have high boiling points. We can think about this as, first of all, most of them are gases, but if there's not gas, you can think of this as sugar. And I can melt sugar in a pan. It has a lower melting point, a lower boiling point. The other interesting thing is our ionics conduct electricity when they're dissolved. Our covalents do not conduct electricity when they're dissolved, and we'll come back and talk about that in another lesson. Do they dissolve in water? Well, salt does dissolve in water. Sugar dissolves in water. That's true because it's polar covalent, but non-polar covalents do not dissolve in water. So all ionic compounds dissolve in water and only some covalents do. And we say like dissolves like. Okay, and here's some examples of ionic and covalent molecules. And we'll get back to that in a second. Now, if I want to determine if it's ionic and covalent, our first thing is to see if it's a metal and a nonmetal. If I have a metal and a nonmetal, it's ionic. Okay, and covalent, the difference between polar and nonpolar, we need to draw Lewis dots or we can do this math. I'm going to come back to the math in a moment. But over here, let's look down here. We have nonpolar covalent and polar covalent. We have ionics, and these are my Lewis dots. Now, our ions steal those electrons like I showed you before, and then we put them in brackets, and we put the charges there, and they bond electrostatically. Okay, so if we do a Lewis dot, which we don't very often with ionics, they need to be in brackets when they're charged. Okay, so we have brackets in the charge. Our covalence, which is what we usually draw our Lewis dot from, is depending if we have pull or no pull. So I want you to think of boron on the beach. Okay, so he's on the beach and he throws a rope to hydrogen, hydrogen, and hydrogen. And we're going to have a tug of war, and we're going to see if the middle atom moves. Now, if all these hydrogens pull exactly at the same time, they all are identical in the amount they can pull. So boron is not going to move off his spot. There will be no pull, which makes it non-polar. Okay? And you can see all these have atoms evenly spaced around, so they will all pull identically, and our center atom won't move off its spot in the sand. Let's look at polar covalent. We do have pull here, which makes it polar. And this pull comes from our electronegativity. Remember, electronegativity is the ability to attract electrons. And that's the pull we're talking about. So let's look at this guy. Here's carbon, and he throws a rope to 3 hydrogens and a chlorine. Hydrogens will pull the same, but chlorine will pull differently. So carbon will be pulled off his spot, which means that we have pull and it will be polar. Now, how do we decide who's pulling the most? We're going to draw an arrow towards our most electronegative atom. Remember, our electronegativity trend goes this way on our periodic table. Chlorine is the most electronegative. So we're going to draw this arrow, and we're pointing to the most electronegative atom, which means all the electrons are going to hang out here. So I'm going to make this delta sign. That means a partial negative charge, because all my negative things are hanging out there. Now we also cross the end of our dipole arrow, because this bottom part, if that's partial negative, this is partial positive. So my electrons are being pulled this way to my most electronegative atom. And we do have pull. Chlorine, if this was a tug of war in the sand, will be pulled. So we have pull, and that's polar. So that's the difference between polar and non-polar. The other thing that we want to look at is how we can do it mathematically. Now, we have ranges here, okay? And if we have from 0 to 0.39, I am non-polar, okay? And if I have 0.4 all the way to 1.69, I am polar covalent. And last but not least, 1.7 plus is going to be ionic. Now, this is a trend that happens. We don't say something is completely ionic or completely nonpolar unless it's way on the exact side. So if I take chlorine and chlorine, I've got two things. The pull is going to be exactly shared equally. I won't have any pull. That's considered completely nonpolar. And I would take these numbers and subtract them. And those are electronegativity numbers, and they will come from a chart. I'll have to give those numbers to you. You don't have to memorize them. And let's see if I can find my chart. Here are my electronegativity numbers. So you'll be given these numbers, and then what you're going to do is you're going to subtract them and see what range they fall into. Now, if something is polar covalent and I get a measurement of 0.4 versus a 0.8, the 0.8 is going to be more polar. I'm starting to get more polar and leaning towards ionic. So this is a continuum. Okay. Some review things we need to know for this is atoms make bonds to make their electron shell more stable. Valence electrons are what participate in bonding. These are notes to take. These electrons are located in the highest energy level, also called the outer shell. We need a full outer shell to be stable, and this is 8 electrons, which is also called an octet. So our outer electrons for neon, we have 8 valence electrons. How do I know that? Because their group number, or 8A, tells me the number of valence electrons. We have exceptions of hydrogen and helium. They are in period 2, and those only need those 2 electrons. Okay, we're going to cross that out.